we're in the second part of the titration. So what we're going to do is we took the definitions. We know what a titration is. We've done them in lab. Now we're going to do the calculations associated with them. Okay, there are only 3 steps for a strong titration. First one is before you add any base, or here we're doing a strong acid, strong base titration. If it's reversed, it's the same thing, except you reverse which strong you use. At the equivalence point, and the beauty of strongs is the equivalence point, the pH will always be 7 for the strongs. Okay, and then past the equivalence point. So before you add it, it's a strong acid, assuming that's what you're titrating. And then you hit the equivalence point, and then it becomes a strong base. So this is really actually a simple problem, as long as you keep up with your numbers. So, again, here's the curve for a strong. Notice that this is the initial. From here is strictly how much you have left. Here's your equivalence point, which is always 7. And then this would be your strong base. Okay, so in this case, we've got 0.1 molar sodium hydroxide solution is titrating 50 milliliters of 0.1 molar HCl. Okay, so we have chosen 4 points at which to do. Now, if you'll notice, if you'll take a minute, this is before 0 base added. This one has 40 milliliters of base added. So this is going to require a reaction. And then this is the equivalence point. And we're going to know that this is the equivalence point because we know that we have 50 mils of 0.1 molar HCl. So that means that if you have 50 milliliters of HCl times 0.10 molar, this is the HCl, then if you have 0.1 molar of the base, in order for the moles to be equivalent, then the volume has to be equal to 50 milliliters. Okay, now that's not always true. It's always true that it's 1-to-1, but it's not always true that it's 50-50. Okay, so let's look at these points. The first one is simple because with no base added, this is strictly a strong acid problem. So you take the negative log of the hydronium ion concentration, which means that the pH is equal to 1. That's easy, no problem. Now, problem with B is we've got the sodium hydroxide. We're going to react it with the hydrochloric acid to produce sodium chloride plus H2O. Now, in this particular case, we need to know how much we have because it's a simple reaction. So, one of the easy things to do is just to take and multiply 50 milliliters times 0.1 molar, and that will tell us in the molar here, we're going to use millimoles per 1 milliliter. So we can just cancel that, and that will give us 5 millimoles of HCl. Okay, that being the case, if we take 40 milliliters and multiply it by 0.1 millimoles per 1 milliliter of the base, then we've added 4 millimoles of our base. So if we think about it, we're going to start with 4 millimoles of base, 5 millimoles of the acid. It is a stoichiometric reaction. So we're going to be left with nothing of the base and 1 millimole of the acid left. Now, we have to find the pH, so we need the concentration of H left, which is going to be 1 millimole divided by my new volume. Okay, so if we added the volume total, if we started with 50 milliliters of the acid and we added 40 milliliters of the base, then that means our new value is 90 milliliters. And again, since I've got millimoles, 1 millimole, I can put it over 90 milliliters and end up with my concentration, which is 0.11111 repeating, which is the H plus concentration. So if we take the pH of that, we're going to find that it's 1.95. So we have moved from a pH of 1 to 1.95. So we're almost at 2. Now, at the equivalence point, we know this is the equivalence point because the millimoles of base is equal to 50 milliliters times 0.01 molar. Whoops, 0.1 molar. Which means we have 5 millimoles of the base. The millimoles of the acid we've already done, but we'll do again, is equal to 50 milliliters times 0.1 molar, which is 5 millimolars. So what that means is you have 0 milliliters, millimoles, whatever, of strong left. So the only thing you have is sodium chloride, which is a neutral salt. So the pH is equal to 7. Okay? Now, the next 50-point question is, on this one is, what is the indicator? Methyl red, bromethymol blue, or phenolphthalein? Well, if we look at the chart, and we did the chart in the previous section, and I think I accidentally deleted it. So if we look at the chart, we find that methyl red has a pKa equal to 5.0. Bromethymol blue has a pKa equal to 7.3. And phenolphthalein pKa is equal to 8.7. So of these two, bromethymol blue would be the best indicator. So best indicator is bromethymol blue. But the inflection point is basically, if you look at a strong, if you'll notice that, it's about 2 to 10. So looking at the inflection point, you'd be okay to use phenolphthalein with respect to this reaction. And that's only because it's a strong. But it would work just as well, so either one of those will work. Now the next question is after we added 50.2 milliliters of titrant. So for the base, we started with 50.2 milliliters times 0.1 molar, which means I have 5.02 millimoles of base. We reacted it with 5 millimoles of acid. And remember, each time we're going back to the original solution, we're not taking the step before. So we're left with 0.02 millimoles of base. And it is a strong base. So now what we need is the volume. So our volume total is going to be 50 plus 50.2, which is equal to 100.2 milliliters. So we put 100.2 milliliters, which gives us a molar concentration of 1.996 times 10 to the minus 4th. So we take the negative log of that, of 1.996 times 10 to the minus 4th, and that gives us 3.6998, which that's our pOH. So our pH is going to be equal to 10.30. So on a strong titration, we've got, before anything's added, as you add things, the equivalence point, and when you pass the equivalence point, is strictly a strong base. Okay? When you have a weak acid, with the strong you had 3. Starting, equivalence, and strong base. But in the weak acid titration, we have 4 steps. The first one is strictly a simple Ka. Now, a lot of times I like to skip to the third one because this is your equivalence point. At the equivalence point is a salt problem. Before that, step 2 is a buffer zone. And then after the equivalence point, you're a strong base, you're back. So we've done Kas. We did that in chapter 16. We've done buffers here in chapter 17, and we did salts in chapter 16. And we did strongs in chapter 16. So the steps are nothing new and exciting. They are everything you've done before, except the beauty or ugliness, your call, is putting it all together. Okay? Now, if you're doing a weak base, it's exactly the same thing except in reverse. You have a Kb, the buffer zone, the salt problem, which is a Ka, and then the strong, but instead of it being a base, you have a strong acid. Now, the other thing you have to always keep in mind is the fact that if you've got a base, you got the POH, and you need to go back to pH, and vice versa. Okay, so when you actually look at graphing the species, and we will actually graph some in the next section, but right now I just want to point out what you see. Okay, the first point is the weak, and it's strictly a Ka. The second point, and let me change colors so you can actually see this, is we said this was a weak acid, so it's Ka. This is the midpoint of the buffer, or if it's not at the midpoint of the buffer, it's in the buffer zone. And then this is the equivalence point, which is a salt problem. And then after that is strictly a strong base. These are the only 4 points you have to graph it, but if you're doing an actual titration, which you will be doing, you'll be given pieces parts. Now remember, these problems and any of the other ones, there are additional videos of just the problems, and there are extra problems posted. If you need more of something, let me know, and I will try to get them up as soon